So, well, it's speculatively related. So, just so that we're on the same page, I want to start with telling you what bond percolation is. So, take an infinite lattice, so z to the power of 2, and let's look at this one. And then what you do is between any pair of adjacent vertices, you may or may not include an edge. And so you have one parameter, the percolation parameter p, and for every pair of neighbors with probability p, you include the edge, or with 1 minus p, you don't include the edge. These are independent variables. And what's interesting is that as you change p, you have obviously more and more edges. So here p is 0.25, I think. It's 0.49 here, 52 here, and 75 here. And what people find interesting about it is that there is a phase transition at 0.5, so between this and this state. And what that means is that on the left panel, you don't see infinitely big components, but in the right, you have enough edges that with probability 1, there will be an infinitely big component. So the individual edges, there are so many of them.
What do you mean by edges? You mean connections between 2 points, or what are
I'm talking about this as a graph. So I'm defining a graph on the vertices of z to the power of 2, so the integer numbers times integer numbers. And between any pairs of neighbors, you either put in an edge or you don't put in an edge into a graph. So you either include a black line or there is no black line.
You mean you connect 2 points or what?
Yes.
So for p equals 0, this is white.
Yes, and when p equals 1, then everything is included.
Lattice, right?
Yes, that's right. That's right.
Lattice,
And so why this is interesting? So one reason is that this can be a model for a piece of rock and cracks in the rock. And so the question is that if you immerse it into water, will there be enough cracks so that the water can flow into the middle and make the central point wet, let's say?
You know that there is a single point, a transition, where you now have a continuous line that has an infinite length.
No, so there is phase transition, and it's in a sharp value of 0.5 in this case. And it is proven that if you're just below 0.5, then with probability 1, so almost surely you don't have an infinite component. So these components are somehow localized. And when you reach the value, then you have, with probability 1 again, an infinitely big component. And interestingly, you have one unique infinitely big component, so there isn't space for two disjoints.
I mean, you're talking about an infinite component because you're thinking of an infinite lattice, right?
Yes, right. Sure, yes.
You don't have boundary.
And what do I want to do? So this is a much studied object in the probability theory, and in order to avoid confusion, I want to say it so that I say that I include an edge or not include an edge is equivalent to saying that the value of the edge is 0 or 1 and 0. And also when I include the edge, I will say that the edge is open versus it's closed when it's not included. And this has to do with this model of cracks in a piece of rock. So open is when it's involved or when it's included. Okay, and now on to biochemistry. So I must say that there were, what did I want to say? No animals were harmed for the making of this project because this is all in vitro biochemistry. So what's happening here is that I have a collaborator back at Freiburg University who's called Günther Roth, and his group develops these lab-on-a-chip devices for many interesting applications. I can give you the website later on, or if you have time I can tell you more. So the experimental setup that they use is that they have this well plate. This thing is about 1.5 times 1.5 centimeter big, and it has about 100,000 little cavities, little holes on it. Each of these holes has a volume of, I think, 19 picoliter, which is 19 times 10 to the minus 12 liters, which may not say much, but so I computed that this is about the volume of 10 to 20,000 E. coli bacteria. And they want to do parallelized biochemical experiments in them. And the particular experiment that he approached me with, or what we're doing here, is a digital PCR. So it's polymerase chain reaction on DNA molecules. And it's called digital because the way they do it is that they have a solution of DNA molecules in this PCR enzyme whatever mixture, which they inject onto this plate without knowing where the DNA molecules end up. But the solution is so dilute that most of these reaction volumes will get 0 or 1 DNA molecules. So that's why it's called digital. It should be called binary or something else. Anyway, so it's very unlikely that you have more than 1 DNA molecule in any of these volumes. And then they close they close this lid on top of it. And they run a PCR experiment. So they replicate the DNA molecules in each of these little spots independently from each other. And then the way they do it is that this lid is actually covered with some kind of surface, I don't know. So the surface is treated in such a way so that primers are attached to it, so that when you do the PCR in one of these reaction volumes, the copied DNA molecules actually grow attached to this surface. And so once you're done with it, you can flip this over, and in this case, they do this with 3 different DNA molecule types, each of which has a specific fluorophore which can bind to it. And so they flip this over, and then they introduce this fluorophore, which specifically binds DNA type 1, and they scan this fluorescent image. Then they wash away the fluorescent dyeing, and they do the second type of fluorescent dye to bind to the DNA type 2, and then repeat for 3. And then you combine the 3 color channels, and so you express DNA 1 with red color, and DNA 2 with green, and 3 with red color. And this is the picture you get. So this shows you how dense the molecules were. And so the point is that each of these spots is the image of a reaction in one of these volumes, and so it is like, I don't know, 10 million DNA molecules dyed with this dye. And so this is what you hope to get. So a nicely uniformly spread out DNA molecules, because you thought that they were evenly and uniformly spread out on your chip. But sometimes what they see is what's here at the bottom, where you see clusters of the same color. So here you see a green cluster, here you see green and red, and somehow there is this mixture of green and red which gives you yellow, and so on. And this suggests that the source of this signal is not a point source, but there is some kind of contamination going on. So what happens is probably that there was a green DNA molecule here which managed to contaminate nearby wells, and that closes this clustering. And what my collaborator asked me to think about is how you could estimate the rate of contamination, of this cross-contamination, by looking at this picture. And so inferring, so if this is your data, try to tell how much cross-contamination you get. And cross-contamination can be seen as what is the number, or what is the ratio of those reaction volumes which were not perfectly insulated but which got contaminated. And so where does this contamination come from? And they say that the thing is that when you close this lid on top of the plate, you sometimes trap air bubbles and dust particles, and then there is this capillary flow of the PCR solution where DNA molecules just flow over and therefore give signals which are false signals, essentially, which you want to avoid. Okay, and what else I want to say? Yes, so microfluidics. There is another technology in which there is an emulsion of, so in an oil medium, people let water bubbles flow one after the other and use these water droplets to run experiments. Whereas my collaborator uses this microarray-like technology, and he says that there is absolutely nothing in the literature about contamination estimation, and his suspicion is that this microarray arrangement is actually much better suited for that than this flow of water droplets in an oil medium.
So there isn't anything that they can do to just avoid this cross-contamination, capillary flow?
To avoid it, I mean, in theory you have a flat plate and you have a flat lid and put one on top of the other and press it on it. They have a little machine that holds it together, press together, but it's unavoidable in the setup.
You could space the actual samples more from each other. If you don't trust that 2 of them are actually isolated, you can put them, I don't know, 3 or 4 away, far from each other.
So this plate is, I think it's called, I don't know how it's called. It's somehow commercially available. It's a next generation sequencing plate by F454 or whatever. And so the size is given, and you don't really control where the DNA molecules end up, because I think the point is that you want to do it fast in a parallel fashion. So you don't put the droplets one by a robotic arm, you just inject the liquid. wherever it ends up.
But if you do it more dilute DNA solution,
Yes.
the clusters will be further apart.
Yes, but then later on, I think they want to use actually 100,000 volumes to run 100,000 different reactions in one go, and they are interested in whether you can do that or what percentage of your signals will be false positives. Right. So So I don't want to talk about what kind of applications they have in mind, or shall I? So I can come back to it in the end.
Sorry, I mean, I don't even understand what the point of, I mean, suppose you have this cross-contamination, what do you learn by doing the top thing?
Will you subtract this somehow then? From
Is this a control, in other words?
What do you get by giving a number? So what I want is a certificate that with this particular technology, with this particular gadget, they can reach 99.99% cleared signals. So like if you have 100,000 spots, then 99.99% gives you the signal that you expected it to give, and there is only 0.001% which gives a...
I mean, what's the basic question that you're trying to answer by doing this experiment?
By doing the digital PCR experiment. This is a technology demonstration, so what they want to do with this equipment is really a long...
Fine, so this is like a control experiment in some way that just, you know...
So here is one thing that they... So I'm not an expert of this because I don't work in their book, but one thing that they want to do with this is, let's say, DNA concentration measurement. So you have a solution of DNA and you want to measure the concentration. How on earth do you start off with? And they say that if you spread it out on this chip, then you can just count how many spots you have, how many empties you have. Okay.
But still, so suppose you estimate the rate of cross-contamination.
Yeah.
You just argued that you can't stop it. You can't
Yes,
get
but
rid
if
of
you
it.
order DNA molecules from whichever biotech company, they will say that this is pure DNA, but it's only 99.99% pure. I mean, it's a useful info to know. There is always error, and you want to have an estimate how much error there is. That's all I'm saying. Whenever you do a measurement, there is error, and you want to certify how good your technology is.
Okay, so if you pulled the DNA out of one of these little vessels,
Mhm.
if it was red or blue or green, it would be pure. If it's yellow, it's
Yes.
contaminated.
But that's not what they want. So they want to do all kinds of different things, which I'm not telling you about. So they want to do rapid vaccine development by, let's say, take a pathogen, break it up to pieces, spread it out on the chip, and take a blood sample from somebody who has survived this disease,
Mhm.
and then spread it on the chip and see what binds to what. And so you know what is the antigen that actually binds that pathogen.
So Bence, you want to somehow quantify the cross-contamination
Yes.
so that your experiments can be as efficient as possible. Is that?
I would say that I want to certify how much cross-contamination there is in this particular gadget, and we use this digital PCR experiment as a tool, as a tool for that, under the assumption that whatever I estimate here will be true, what kind of biochemical experiment I want to run in this.
Ultimately, you need a number, right? For each
Yeah.
spot there, you should be able to say, it is a green signal indeed, and I'm confident, I get 95% of the chances it's going to be, of the cases, it will indeed be a green signal. And you have to what you're trying to do is just quantify.
But there might not be green signals. There might be that there is one signal out of 100,000 spots, because whatever you run is like trying to find what is the molecule to which your antigen binds. There won't be colorful spots. There won't be 3 kinds of colors. There will be 100,000 different colors.
I just gave green as an example. You just want to
No, so that's a different question. What I want to do is that, given that you make 100,000 measurements in parallel in one go, can you give a percentage, what percentage of these measurements are actually accurate and what percentage of them are unreliable? I won't be able to pin down which are the correct ones and which aren't. Okay. And so this is the question. Okay, that's how he came to me. And then you have to come up with a mathematical model for this. And so there are at least 3 aspects which you might consider here. One is whether the contamination is uni or bidirectional. So if vertex I contaminates J, then is it inevitable that J will also then revert reversibly contaminate I, so that would be the symmetric case, or can the contamination be one directional? Okay, the other question is, so I started with percolation theory, so this is what I had in the back of my mind, that is the model that I want to use. So the question is, are the edges which you include in the graph independent from each other, or are they locally correlated 0-1 random variables? So you might say that because the cause of contamination is these trapped air bubbles and dust particles, if there is contamination somewhere, then there will likely be contamination around it, because the dust particle is just big and it causes many contaminations in a cluster. And then the other question is this contamination confined to neighbors, or does it propagate via a series of open edges, so via the edges which are included in my graph? So while you're doing the PCR, these DNA molecules float around and float into the next volume, and then they start the PCR experiment in the next one. But is it possible that they actually contaminate far away places, right? So that they just float over and over, diffuse to more and more cells. Okay. And so if you look at this model, which is highlighted in red, so contamination, so the main thing is that if I assume that contamination is confined to only neighbors, and these edges are independent Bernoulli variables, and whatever about directionality, then this is actually a simple problem because it's just a combinatorial calculation, because whatever happens is dependent on one volume and the neighbors, or on two and their neighbors. So this is something where you can compute the, well, you can use the method of moments and compute that, express everything in terms of the parameters.
You'd be collecting those two C's that are neighbors. Or you can correct that, I guess.
It's easy, anyhow. And what is not easy, but what I focused on, is what happens if the contamination is strict, so symmetric, and it has the property that contamination might propagate via a series of open edges. And I chose this model to focus on because this is exactly what you get if you start with the percolation, so the bond percolation that I showed at the very beginning. Okay, and so here is the...
When you say, sorry,
Yes?
local correlated 0-1 random variables, you mean that this models whether you are connected or not?
Whether the edge is included, so the
Yes,
edge
whether
has a
the
value
edge
of
is
0 or
there.
1, and the 1 is if it's open.
Are they correlated in what sense?
So in the standard percolation,
Because
each edge is
it
independent
a
from the
model,
other.
Yes,
So that's a...
right.
What is the modeling assumption? That's the question. Yeah. And of course, I don't know. I mean, whatever you choose to be your model. Okay, so I define a spatial stochastic process, but it's not dynamic, it's static in time, okay? To describe this, of what is happening here. So I have NC colors, so the number of colors is NC, in this case it's 3. And these spots are the vertices in my graph, and for every vertex in my graph, I have 3 independent Bernoulli random variables, so it's 3 flips of coins. I have these 3 global parameters for the 3 colors. So I have a parameter for blue and one for red and one for green.
Do you need the colors? Why don't you start as one color? Does it not make it easier?
It doesn't make it easier. It doesn't make much difference. You can do the same. You can do the whole process with one color as well. It's just I'm doing this way because that's how the data comes. So you have 3 parameters for the 3 colors, the intensity of each color. So the probability that any given vertex gets the color blue has a value, and this value is same for another vertex elsewhere in the graph. And so for every vertex, you flip 3 coins independently from each other, and then you flip 3 coins for another vertex. Those are independent as well. And so you get this, what I call the seeding. So this is how the DNA molecules, the DNA templates, end up in the reaction volumes when they inject in this solution. That is what it's supposed to represent.
So that's the ideal case, right? That's the non-contamination
Yes,
case.
that's non-contamination case in a way. So I call that seeding. And then the important observation is that you get mixtures of colors. So blue and green together make cyan, and then you see actually the cyan colors. So a vertex can get multiple colors, and you observe all of these colors. That's the assumption. And this is on what is called a triangular lattice, so it's not a square lattice, and this is the bond percolation. So independently from the seeding, there is this bond percolation going on. So there is again a probability which I call mu. For every pair of neighboring vertices, I either include an edge or not include the edge with probability mu. Yes. So this gives the edges where contamination potentially happens. And so I put the two together, overlay them.
Is it one directional or?
So it's bidirectional, because I want to use the bond percolation as my framework.
Like always bidirectional or optional? I mean,
Always. Whenever you have an edge, it is bidirectional by definition. And so this is what you end up with. I just overlay these two together, and you get this picture. And so let's say you have here a case of a red spot and two edges, and what ends up happening is that that red spot contaminates these two vertices with this red color, and you get these on here. Or you get here green and red together next to each other. They are connected, and they are also connected to this guy and that guy. And what happens is that the green contaminates the entire component, the red contaminates the entire component, and so you get yellow, 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 because that's their mixture. Okay. And so the task I face now is that, given this picture, I want to estimate the 4 parameters. So the percolation parameter from here and the 3 seeding parameters from here. Okay, these are parameters of these variables. And all I have is this picture, and I don't know where the edges are, and I don't know where the original spots were.
how accurate is that realistically? I mean, it seems like your green and red, it wouldn't actually be 4 equal yellows, it'd actually be one sort of slightly reddish, mostly greenish.
So I don't know. So as you see, I use variables which are 0 or 1 valued and not real numbers. So you could introduce like intensity levels and more complication. Surely it would probably be more accurate. It would be harder to deal with. And the nice thing about this is that I can prove a very exact statement about my estimation method here.
So more or less you're curing just where the contamination is, not how contaminated.
Yeah, so I don't want to predict which are the spots which are contaminated. I don't try to do that.
This is a PCR experiment, so
Yes.
the DNAs are getting amplified.
Mm-hmm.
So I think there's going to be equal amounts of, say, green and red in the volume after a number of rounds.
The issue is that as you run the PCR experiment, so let's say you run 20 cycles, and what if the DNA molecule contaminates after 5 cycles? And so in the first volume you have 2 to the power of 20 DNA molecules, and in the second you have 2 to the 15.
Yeah.
Something like that. So you could actually infer the history from that, perhaps. But okay. And so that's what I want to do.
Somehow you have 2 types of contaminations, not here. One that spreads, and the yellow should also not be there at the beginning, because it should be pure everything.
I don't call it contamination.
But it's
Like you mean if one volume is seeded by 2 different DNA
yeah, they
molecules?
should also not be there. I mean, it should
Yes.
Yeah.
Yeah.
Yeah, but it's somehow this also then somehow interferes with the thing, the other yellow that you see when they have contamination due to because they're connected. If they would
I mean,
be pure, then you would
problem.
know that this is a contamination yellow one. But if the other one is not pure, then you don't know if this was from the beginning or it was because of the connections.
So now I have a stochastic process. Well, it's a process in spatially, not in time. So it's a static thing. So my index set is capital I. The number of elements, the number of vertices is ni. So this is 100,000. I have nc colors, so in this case 3. And so xil is the state of vertex I, and whether there is color L in that vertex or not. So this is its value is 0 or 1. Okay, and YIL is what is observed, so this is data, and this is just the maximum of whether there was, so whether you observe color L in vertex I is just the maximum of these values, so whether there was a seed of color L in I, or whether this I is connected to some J, such that the J got seeded. Okay? And the goal is to estimate this parameter vector, so the rates of the colors and the rate of the percolation from the data YIL.
Those are all numbers between 0 and 1?
These parameters, so these are all Bernoulli random variables, so yes, they are all these are all flips of coins, essentially, with biased coins with these parameters. So yes, they are between 0 and 1. So there's a probability that you have a seed or not have a seed, have an edge or not. Okay, and so the method I use is called the method of simulated moments. And the objective is that I want to prove that this method of simulated moments is a strongly consistent estimator. That means that it converges to the true parameter value with probability 1. As, yeah, so I'll come back to that, as the size of the lattice tends to infinity. And so, in order to do that, I will have to prove a strong law of large numbers with weakly dependent variables. So, yes, I'll come back to that. Okay, no, sorry, say it now. So, so the strong law of large numbers. The law of large numbers says that if you take a big sample, big independent identically distributed sample from whatever probability distribution, and you take the average, then this will converge to the expectation, so the mean of your probability distribution. The problem here is that if you take these y's are not independent because they are connected by edges potentially. Okay? And therefore it's not the usual way of proving the SLM. And what you need to do is you need to upper bound the dependence between faraway vertices, so their correlations. And for that, I use percolation theory.
Why are you saying that they're weakly dependent?
Well, they are dependent, and I say weakly because those who are far away from each other are
Yes,
almost
they're far away,
independent.
yes,
So the probability that they have influenced each other is very low.
So, yes. Also, while we are still at this slide, is there any chance for since you mentioned the law of large numbers, is there any chance for a central limit theorem result that will give you confidence intervals for your thing?
I'll come back to that. Unfortunately, I can't do it, but yes, I'll tell you why I can't do it.
So your estimation problem to a biologist would be how many spots of each color should there actually have been if there weren't contamination, and what's the probability to contaminate a neighbor?
Sorry? So I want to tell what the density of the DNA molecules were. That was the lambda. Those are the lambda parameters. So, I mean, they will know what concentration of DNA molecules they want to introduce to the system, but I don't trust them, and I want to estimate that as well. Okay. And what I want to do, so the method I use is called the method of simulated moments. So this is a frequentist technique. It's not Bayesian, and so this is a generalization of the method of moments. And so, what is the method of moments? It is a very well-known thing. So you have what? So you have some data, calligraphy Y, and you take a function of this capital Y, which is, let's say, an m-dimensional. So these are the moments. So these are some generalized moments. So you should think of first moment, second moment, and so on. And I take m of these. So that's the number of moments. And you have another thing. You have a model, which is parameterized by some theta. And under optimal circumstances, you can compute the expectation of exactly these moments as a function of theta. Right? This is the method of, and in the method of moments, what you do is you set these two things equal, and you solve this equation, and that gives you your theta estimate. Okay. And so what you need to have is that you should have as many moments as how many parameters there are that you want to estimate. Okay. In my case, the problem is that I have a model, but I can't compute the moments, because in order to compute the moments, maybe I should say what moments I want to use. So I want to use the following thing. So y I L and y I L and y J L so for every color L, I want to look at these things. So how often I see color L in my vertices, and how often I see that color L appears into adjacent vertices I and J. And so for each color L, these will be the coordinates of my function, capital K. But in this case, I cannot do that. So what I do instead is that I simulate the system. So that's why it's called not method of moments, but method of simulated moments. So what happens is that I propose parameters. So I propose theta 1, theta 2, theta 3, and so on. And I compute. So from the simulation, I simulate some capital Y, and I compute this ky for that.
You want to put a hat on that?
Hmm?
You want to put a hat on the K?
Yes. No, because it's the same function. It's the input is different. So the calligraphic Y was the data, and Y comes from the model. So it comes from the simulation. And what I do is that I actually not just simulate one, but I simulate S equals 1 to ms, so many, and I take their average. And what I do is that I take the difference between this guy and this guy and try to minimize this in theta. So I explore my state space by proposing new theta values. I always compute the moments instead of actually explicitly in the closed form computing the moments. I do simulations, compute the empirical moments from the simulation, and try to minimize the difference between the k that comes out and the k that came from the data. And I try to minimize this over parameters. And so then this becomes a, what does it become? It's a global optimization problem on the state space. And so I don't have much to say about how I propose these thetas. We've implemented this in MATLAB, and whatever global optimization routines there are in MATLAB, that's what we use. And there is one more interesting thing to note here, is that as you go around the state and your parameter space and you try different thetas, you might come back to a place where you have been before. And so in order to be consistent with what you've done in the past, we use, or it is recommended, and we follow this recommendation, we use common random numbers. So our random number, so the source of randomness for this is drawn at the beginning, so some uniform random variables, whatever. So this is a big vector of random numbers. And this is the same source of randomness is used for every proposed parameter value. Okay? Because if you drew new random variables for every theta, then you would see it would just cause you fluctuation that you would rather avoid.
Bence, how do you constrain the models that you, isn't there an infinity of potential models that you can choose from?
I specified what my model was.
You do? Okay.
So
Then could you specify that differently?
So what I'm saying is that this is my model, and this is the model for which I do the parameter estimation. And so the
given-
parameters give
Given
me...
your model, you're trying to find the best parameters
Yes.
within that model.
And
How
what
many
I'm-
parameters are you estimating typically?
Well, in this case, 4. I have 3 colors, so that's 3, and 1 for the percolation. 1 percolation. So it's a search in a 4-dimensional space, in my case.
Do you ever go back to change the model?
So that was here in the beginning. So what are your modeling choices? And of course, I mean, you are all familiar with this. When you have a particular problem in nature, then you create a model, and then you study the model. And then, of course, everybody can question how good your model is, and you can go back and refine it and tune it.
And how many moments are you going to use?
So the moments are these guys. So that and that one, and I have 3 colors. So there are 3 of these moments and 3 of these moments. So I have 6 moments, and I'm estimating 4 parameters. And I do this by minimizing this distance, or squared distance actually.
Square distance.
Okay. And so this is the theory for the method of simulated moments. So this is what I said. So there is this, your data calligraphic y, unknown parameter theta naught. You have some n-dimensional function k, and then its expectation under the parameter theta is k theta. And so there is something we must assume, which I hope holds, but I can't prove it, myself, which is called identifiability, which means that so if y is drawn from the true parameter value theta naught, then this moment will only be the same if theta is actually theta naught. So what this is saying is that the moment is, so from the moments you can invert uniquely back to the parameter. There is only one parameter, which is theta naught, which is giving you the same moment as the moment what you get if true parameter is theta naught. It's called identifiability. Okay, and so the reason why we're using the method of simulated moments is that the expectation of these moments, or the expectation of this statistic k, is not available in analytical form, but we have an unbiased estimator, so we can simulate it using these UIS random variables, so pseudo-random numbers. Okay. And so so I define here this alpha quadratic form, so this function with an omega symmetric positive definite matrix, and I put so these differences for every moment go into this alpha quadratic form, and so this is my objective function. So the alpha applied, so this quadratic form alpha applied to the difference between the moments of the data and the moments of the simulation, where I run NS simulations, and my estimator is the argument in theta, which minimizes this difference. So this distance function, which is this thing, right?
I understand what that sum over S is doing.
So I run NS simulations. So for
NS
each proposed,
simulations.
yes, for each proposed parameter value, I run not just one simulation, but 20 simulations, and then average over them to get this. Okay. And so this is the general statement about the method of simulated moments. So you start off with this symmetric positive definite matrix alpha, and then define the MSM estimator with this formula. So you try to minimize this quadratic form of the distance between the measured or the data, so the real data, and your simulated data over NS simulations. And then the statement is that if something holds, then this will be a strongly consistent estimator, which means that your estimator converges to the true parameter value almost surely, so with probability 1. And the conditions are that it has to be identifiable, so it has to be the case that there is only one parameter value which so the mapping from moments to parameter values is unique. It's uniquely defined. So if you know the moments, then those uniquely define what your parameter must be. Another interesting thing is that, so Ni, so how big my sample is, that tends to infinity. So how big my lattice is, tends to infinity, but Ns, that is how many simulations I run for every proposed parameter value, that is fixed, so that is bounded. It doesn't have to go to infinity. So it can be 20.
Will you choose this?
You can choose it, it's a user
How do
input.
you choose it, or just by?
Trial and error, essentially.
And so you have 4 parameters, each between 0 and 1, and then you just discrete choose, let's say, 1, 10 for each parameter, and you have 10 to 4, and then you run 10 to 4 times 20 simulations? Or?
No, for every parameter value theta, you have to run 20 simulations.
Yeah, but theta can be, so it's from 4 parameters. No? It's
Be very dynamically, not on a grid.
Oh, and what's this matrix capital omega?
Omega. So that's a weighting on. So what I'm doing here is that my k has this many dimensions.
Yeah.
And when I say that I want to look at the difference between those things, I can decide how to weigh different coordinates.
Right.
So I might put more weight on something which I have
So
more
that's
trust in.
another arbitrary thing you have to decide on how you're going to weight the.
Yes.
What if you took NS to infinity instead? Would that work? Fix Ni and send NS to infinity.
I don't know.
Okay.
I don't know
Correct.
now.
But the actual setup is what Pete is referring to, right? I mean, your
The issue is, okay, the
fixed.
issue is that your data is always a finite draw, so it's never a perfect representation
Your
of
lattice
the,
is fixed.
of the probability distribution, and therefore it is important to take n to infinity. That's why.
It's important to what?
To take the size of your sample to infinity. I mean, in standard statistics, if you want to estimate a parameter, what you always have to assume is that your IID sample, the size, it tends to infinity. It's not enough just to run more and more simulations in your computer because your data sample is finite and therefore it won't be a perfect representation of the abstract probability distribution from which it's
Well,
coming.
that's why you need a central limit theorem to tell you.
It will tell you something about how far.
Give you the confidence interval of your prediction.
Yes, yes,
Central
yes.
limit theorem.
Okay.
And you're just going to use some standard minimization algorithm
Yes,
on MATLAB?
Yes.
With
Yes.
an initial guess, and it'll search around and
Yes.
hope
And hope it works. Yes.
some global optimization.
Yes. I do it with multiple starting values or initial values. I mean, it should help a bit. Okay, and so the challenge is that, oh, and what I should say is that, so, and then the strong law of large numbers is, what is this saying is that the strong law of large numbers for these moments as ni tends to infinity, right? So this should be uniform in my parameter value for every simulation S. So that is also a condition which has to be satisfied. And in my case, the problem is that my variables are neither identically distributed because of boundary effects. So vertices on the boundary have fewer neighbors than vertices in the middle. And they are not independent. So then both of these assumptions of standard statistical methods are gone. So these are the moments that I want to use. Like I said before, for every R color, I look at the density of seeing a color. That's the first one. That should tell me a lot about the parameter lambda, and how often I see the same color in two neighbors. So these are 0, 1 values. So this is either 0 or 1, and it's 1 only if both yi and yj are 1. So how often I see the same color in two neighboring vertices should tell me about the contamination parameter. Okay, and then there is this issue of identifiability. There are extreme cases in which the problem is not identifiable. So if all the edges are open, then you will always see white color. Or if the intensity of seeding is 1, then you will see blue everywhere. And then if that's the only color, you won't be able to infer anything about the parameter of percolation, right? So the contamination. Okay. And so this is the main result here. So I introduce this I2, this is the set of pairs of neighbors in some kind of ordering so that I only take pairs once and not twice. So I want to rule out ij and ji both being in the set. So I have some whatever positive definite symmetric matrix. I define this distance through this quadratic form. I choose theta to be a compact subset of, so this is my parameter space. So lambdas can be anywhere between 0 and 1, except that I don't want this extreme case when all the lambdas are either 0 or 1 values. And the parameter mu, which is the bond percolation parameter, has to be in the 0 to PC interval. And PC is the critical value or critical probability of percolation. That is what I said at the beginning. So this is the value above which you have an infinitely big component, and even at the value PC. And so I want to rule that out, and I focus on the subcritical regime, where almost surely all the components are finitely big. Okay, and so its value is known for these lattices. So in the case of the square lattice, it's 1/2. In the case of the triangular lattice, that is what I used as the dual to the hexagonal tiling that my collaborators use. It is this value. And so the statement is that if identifiability holds, which as I said I could not prove, but I'm pretty confident about it, and ns, so the number of simulations is fixed, and ni, so the number of vertices tends to infinity, then using these moments of the vertices and the yj's, and comparing the data to my simulations, taking an average, and minimizing the distance, so this estimate will be strongly consistent. So it will converge with probability 1 to the true parameter value. That's the statement. And I'm afraid I wanted to prove this, but we haven't got much time. So this is interesting because, okay. So I want to prove these two statements here at the top, essentially, that the average of yi's converges to the expectation of yi, and the average of yj's converges to the expectation of those. And instead, and this all uniformly in the parameter value theta over the entire theta. And so let's look at this one. This is what I'm trying to prove now. So the average of yi's and the average of the expectations of yi's converges to 0. I rearranged this because of boundary effects. I can't assume that all my yi's are identically distributed. So I take their expectations individually. And so what we do is that's the standard way of proving the law of large numbers. I define this sequence, so it's a geometric progression. So you pick an a which is a little bit bigger than 1. You take a to the power of n and take the integer part, and this will give you like a very fast-growing sequence of integer numbers. And then sk is this sum of my variables. And so if you have ever seen or taught how to prove the law of large numbers, you take this sum and you want to prove that this sum is finite, so that you can apply the Borel-Cantal lemma, and that will prove you this thing. So this is essentially the law of large numbers. And what's interesting here is that, so SKs are the sums of your variables. If you look in detail what these are, you have the sums of the variances of your individual variables, and you have these covariances. So usually when you're in the standard statistical setting, you don't have this second term because your sample is independent. And so the challenge in my case is, okay, so to prove that this is fine, so what I want to do is to prove that this sum is finite, because then I can use the Borel-Cantal lemma. Okay, and so this is the sum from the previous page. And so in the first case, you see that the variance of yi, because yi is a 0 or 1 valued variable, so its variance is at most 1. And this sum of kn elements is at most kn. So this sum will be this sum of 1 over kn. And just remember that this kn is actually this geometric progression rounded off. And so it's easy to prove that this is finite. And so what's interesting is that you want to prove, so you want to be able to use that on the other side of into the second term. So you want to prove that this sum is at most order kn. Okay? And for that, this is what I need to prove. So that is explicitly bounding the dependence between faraway vertices. And you see that there is a sum for all I and j vertices in my lattice. So you take your lattice, and I runs through all the vertices, and j runs through all the vertices independently from that. And so if you sum for every pair ij, these covariances, these must be bounded by whatever means. And so I and j, so how many ways can you choose 2 elements from n elements? That scales as n squared. And you want to prove that this doesn't scale as n squared, but it scales as n. So that's the challenge here. Okay. And so that is where percolation theory comes in. So I want to use results from percolation theory to be able to upper bound these limits.
So in reality, you need some sort of decorrelation, right?
Yeah.
This is what the previous estimate demonstrated.
So what I want to prove is that that the correlation is small. And I'm not interested in individual correlations, I'm interested in summing all the correlation. And then must be that. Okay. And so if you go back to the percolation graph, so the way you define it is that you define a big vector of 0, 1 values. So this is your state spacing. And the measure is that for every, so every edge S, its value is either 1 or 0, and its value is 1 according to some number PS. So what I'm saying here is that you can define the percolation so that for every edge you flip a coin in such a way that the coin flips have different probabilities. So the probability doesn't need to be universally P, but universally mu in my case. And this is important because I want to define my model as a percolation graph such that, so the coloring, the seeding, will be defined by loop edges. So in every vertex, I say that I introduce a loop edge so that if this loop edge is open, so if this loop edge is included in the graph, that's supposed to represent that there is seeding of color, whatever, in my graph. And so these loop edges will have a different parameter than the edges which represent the bone percolation. Okay, that's why I need a little bit of tinkering. And so there's another notion which is an event is called increasing if it satisfies this property, and so that if you increase omega, so omega is the vector of open edges, so it's 0, 1, and 1 when the edge is open. So if omega is part of the event, then if you just open more edges, then it will still be part of the event. And so the statement, there is this statement called FKJ inequality, which says that if you have increasing events, then this inequality holds, which is good because it looks like the sum that I want to upper bound. But then this is actually not what I want. What I want is this inequality to be in the other direction, in a way, which is something you can't get. And so it is another notion which, when you have two events A and B, then they occur disjointly if the reason why they occur is independent from each other. So I should say something about this. So let's look at a finite number of n edges. If you have two increasing events which depend only on these n edges, then let's take this set J, which tells you which edges are open. So this is just the set of edges which are open. And so we say A and B occur disjointly if the reason why A and why B occur are disjoint sets from each other. So it says that there is a set of open edges H, and there is a complement set JW such that the edges in H force A to happen, and whatever is left out forces B to happen. And A and B are increasing, so it means that if you include more edges, then it will be even more true. And so the classical example for independent occurrence is when you have set A is that two vertices X and Y are connected, and set B is that two vertices U and V are connected, and in the bone percolation graph. So that is, let's say, that is event A, and then these are increasing events, meaning that if you put in more edges, then if A already happens, then by putting in more edges, then it will still happen. And let's say U and V are here. So B is the existence of the path like that. And so disjoint occurrence is when you can partition your edges into two sets such that that they are disjoint sets, causing one thing causes A to happen and the other thing causes V to happen. So this configuration is disjoint occurrence because there is no shared edge between them. And joint occurrence would be, so the opposite of this would be if they would share edges along here.
And not have an alternative non-sharing path.
And not have an alternative non-sharing. So it would, yes. So it could, so that could also be in the, so that is also a disjoint occurrence, right? So these two are disjoint occurrences, this is the joint occurrence. And so the thing is that for disjoint occurrence, there is this inequality which holds. And so you can put the two next to each other, and this says one is a lower bound and the other is an upper bound for something similar. So both bound the co-occurrence of the events. It's just that this is not the co-occurrence, this is the disjoint co-occurrence. And so the point is that this event is just the probability that things happen this way. And so this is exactly where the FKJ inequality can be applied. So that gives a lower bound. And the upper bound is given by the BK inequality, but it only upper bounds the disjoint occurrence. So what you do is that the co-occurrence can be separated into disjoint co-occurrence, and this is the joint co-occurrence. So this is the disjoint co-occurrence. So the disjoint minus this product is upper bounded by this BK inequality, and therefore what you're left with is this joint co-occurrence. And that is what you want to upper bound in order to prove that my sum converges, or my sum is order n. And the point is that So what I'm left with is the joint co-occurrence of this and this event. And the co-occurrence of these guys, which is joint, which is not disjoint, is one where I and j are in the same component, where I and j are connected with each other. And so what I end up having to prove is this statement. And fortunately, so as it was pointed out to me on Friday, you can prove this for the entire subcritical regime by using this theorem, which says that the cluster size is, so the probability that you see a cluster which has at least k elements is decreasing as an exponential function. And that means that this sum is just upper bounded or majorized by this sum of a geometric progression. And so this is actually a constant times n. And so this proves the statement. Okay, so this is what I proved, the FKGN. So I proved this one, and this is good because that gives me that upper bound so I can use the Borel-Cantelli lemma. There are technicalities, which is that we've only proved it for an increasing sequence of geometric progression, but you need to prove it for every value in between. And the other thing is that we have to repeat the same thing for not just yi, so not just the first moment, but also the second moment, which is this one. Okay. And then these are the so implementation. So I supervised the master student, Felix Beck, who ran these things implemented and ran it on MATLAB. So these are the results. So these two panels. In the top panel, you see that we had 625 vertices. In the bottom panel, we had 250 vertices. This theta naught column is the true parameter value, this and this. So the first three entries are the three colors, and the last entry is the color or the bond percolation value. There are these three user inputs, how many simulations you run, so the NS for every parameter value, how many initial values to use for the optimization runs as you explore the state space, and mu max is what you expect to be the maximum value of the bond percolation parameter, because we want to do the optimization on a bounded set. Okay, and so these are the values that the estimator gives, and these are the relative biases. So this tells you how many percentage off we are. And so for 625 vertices, we get down to accuracy of, let's say, 30%. When you go up to 250,000 vertices, and the accuracy is about 5%. Okay. And so this is the summary. And let me just say that, so there are open problems here. So one is the question you were asking, can you give confidence intervals? And the answer is that I cannot give confidence intervals, unfortunately. So I can only give point estimates and run tests on synthetic data, so like what the two tables showed, to have a feel for how good the method is. And the reason is that in order to, so under good circumstances, you could prove asymptotic normality with a non-limiting variance in this case. And if you know the limiting variance that's expressed in terms of omega, so you could choose omega optimally by estimating it. So you could choose the omega, which gives you the smallest variance, so the fastest convergence. And so that's something that you were asking about, how to choose omega. But I cannot do that, and it is because my estimator is not continuously differentiable with respect to the parameter, because so my simulation involves discrete variables, so zeros and ones. So I simulate like 0, 1 value for the seeding, 0, 1 value for edges being open, and therefore, as you change the parameter theta, once you have fixed the random variables, there will be jumps in the values, so it will not be continuously differentiable. Okay. So second point is that if you want to be Bayesian, the approximate Bayesian computation can very easily be, so my method can very easily be adapted to be an approximate Bayesian computation by, so what ABC does is that you, instead of minimizing this thing, you pick an epsilon, and you say that this difference should be smaller than epsilon, so you have a prior distribution to propose these thetas. So you propose thetas with prior distribution, you run the simulations, you compute the distance between your simulations and the data, and you say that if this distance is smaller than an epsilon that you fixed at the beginning, then you accept the parameter, otherwise you reject the parameter, and you draw a new one. And that gives you a set of parameters which you have accepted, and that set of parameters will be a good approximation of the posterior distribution. So there's the ABC paradigm, and like I said, it's very easy to modify my method to do that. There is a reason why you can't do maximum likelihood estimation, and it is that you need to do some combinatorial calculations, which I don't know how to do. I don't know how good the model fit is. So like I said, there is every reason why you might want to consider locally positively correlated open edges. And because it all comes from like trapped air and trapped dust particles. And then this is the question that I was alluding to at the beginning, that so I have this very explicit bound on the long-range dependencies between what happens here and what happens here, and that allows me to prove the strong law of large numbers in the case that the effects drop off exponentially as a function of the distance. So the probability that an edge is open is mu, so the probability that two edges are open next to each other is mu times mu, so it's mu squared, and then of three edges is mu cubed, and so on, so that scales exponentially. And so what this is saying is that if the effects drop off exponentially as a function of distance, then on a big plate, it is still like this long, it's still like an independent sample. So the strong law of large numbers still holds. And that is what I have proved essentially, and I've proved it in a rather explicit way. And I wonder if you can extend this argument from the static model to a temporal model. So you do space and time discretization, and then somehow prove that as you progress through time, the effects are small. And so this is some synthetic data, just so if you want to have a feel for how these things look like. The red, green, and blue parameters are these 0.02, 700s, and 500s, and on the left panel, the mu, the point percolation parameter, is 100s, and on the right is 600s. So this is what the pictures you get from there. And thanks to for your attention, for my funding from the AXA Research Fund, and Günter Roth and Christine Rath for the experimental setup and data, and these three people for help with the mathematics. Thank you.
Any more questions?
Yes.
Unless you want to take a question, give the shadow an opportunity to ask a question first.
Yes, please ask questions. You should ask the audience whether they want to sit through more questions.
No, sorry.
Okay, so the is there a chance that you could argue for identifiability by a monotonicity argument?
I would think so. So I think that if you have just one color, then you should see it from how big clusters you get, how big the parameter mu is, right?
I'm saying, is there a possibility you could make a soft, rigorous argument for identifiability using monotonicity?
Well, that's what I'm saying.
Yeah.
Like if you can identify it using one color, then it's even easier for multiple colors, isn't it? So, well, that is also some kind of monotonicity. And then I have this intuition that as you increase the parameter value, you would see what I show on the first slide, which is how to go to the front. So, you would just see the difference between very dense, like this one, kind of. If you fix the seeding rate and increase the percolation rate.
Something that I'm just figuring, like you could sort of say, like it's impossible if I had two different theta hats that gave rise to the same moment, then there'd be one of these moments you're looking at. They could sort of argue, well, it can't be because it'd be bigger for one than the other.
So I don't want to solve it here on the fly.
Yeah, that's fine.
Yeah, I mean, yes, I have the feeling, so that I'm pretty comfortable that it's so confident that it should hold, but I don't know how to prove it.
So following up on a suggestion that John made, if you dilute your sample in the beginning quite a bit,
Yes.
to the point that you get very small amount of signal, so that
Yes.
there's going to be clusters that are quite removed from each other,
Yes.
then you can instead of counting green wells, you can count green clusters. And that can give you an estimate of the lambdas. And also by comparing how many clusters there's with just one well versus how many clusters with two or three, you can estimate the mu. So by doing this, you can experimentally more or less estimate the lambdas and the mu's. Moreover, it can give you an estimate of whether if you see lots of clusters that are very big, it can give you an idea that the percolation events are not independent, that are really independent, that you can have correlations.
Sure.
So I don't know, maybe this could be something that you can even implement experimentally.
Yeah, so that's another question. What is somehow the most informative lambda to infer mu or something like that? That's what you're saying. So there are, yes.
Did you apply this now to the experiment? Did you find out how much is the contamination from the data now that you know?
So no, due to, well, only once. So my student applied it only once, and it's due to technical reasons, which is that we don't have enough data. And we actually haven't solved how to, so once you have the JPEG image, how to turn it into a matrix of values. So that image processing step is outstanding. So we
Or you
haven't
don't know
got to
yet
change.
what is.
So we don't know yet, but like I said, so the point of the picture in the end was that, so this is experimental data, and there were these pictures at the end, which I showed to you. I really don't know why it doesn't jump to the end. So these pictures look very similar to the experimental data, right? And these are synthetic data, so I know the exact parameter values, and so
And if you chose
it
your
gives you a feel
simulation,
for how big the values should be.
you might have said it was when you matched your synthetic data size to the experimental data size, your errors were how big?
So that's the other thing. So the pictures we had about 2,000 vertices.
Okay.
The entire plate is supposed to have 100,000. So I imagine we can go down to 10% error rate or something like that. So under the model, but of course the model is never correct. So. And okay, so the other thing is that I estimate the brunt as mu, but I can also estimate an upper bound on how many vertices are in non-trivial components, which is perhaps more important. So that gives you the percentage of vertices which are potentially contaminated. Okay.
Thanks.
Thank you.